Hi everyone.
Hello.
This class just keeps getting smaller and smaller and smaller, but everyone's still enrolled online, so I don't know. That's okay. You just love hearing me talk. Just kidding. So today we're gonna talk about the chi-square, and I made a fun activity for you guys to do so that when you do the homework, you know how to do it, and you're not like, what? But there's also a lecture that kind of goes over what SPSS is doing behind the scenes. So the stuff that's in most of the lecture, you're not going to have to actually do all the calculations. So don't get too super scared with all of the formulas. I just want to show you how to do it. And I graded homework 4. I'm almost done with 5 and 6. They'll probably be done tomorrow. And I'm working on all the discussion boards. So I should be caught up by like Wednesday with grading. So fingers crossed. Remember that homework 7, which is about independent and paired t-tests, is due next Monday. And then the homework 8, which is on the chi-square, which we're talking about tonight, is due the week of Thanksgiving, that Monday. And we won't have class that Monday of Thanksgiving week, but I will be available if you would like to come and hang out with me and talk about statistics stuff. You just have to let me know. Because if no one wants to come and hang out, then I'm not going to stay here. But if you do, I will answer questions. And I'm also going to post a recording of the walkthrough for homework 4 of how to do it in SPSS with voiceover this time. So that will help, I think. Any other questions so far? I know I'm a little behind. This semester has been a mess. So we'll see what we can do the rest of the semester. Go from there. Okay, so the chi-square, yay! This is what the course objectives and student outcomes are based on the syllabus and the fancy things that you need to know in order to get your degree. Cool. So a review of the t-tests, just to remember, there's 2 IV, independent variable categories, for independent t-tests and paired t-tests. The relationship for an independent t-test means, this first box here, means that the categories are independent. You can't be in both of them at the same time. For the dependent variable, lies, independent variable. Whew. Then for the paired t-test, the independent variable is paired, or they're dependent on each other. So before to after a program in 1 year versus another year, they're the same people measured at 2 time points. The DV is always measured continuously for t-tests. I was looking through, I think I got through half of the discussion board posts, and some of you were close, or you were talking about what we're talking about today, which is awesome, but it wasn't an independent paired t-test. But that's okay, because I think everyone who's here did it, so good job. Questions about t-tests right now? Okay. And again, I don't expect you to be doing these by hand. Use SPSS because it's way faster. Okay. So this funny looking symbol down here is the chi-square symbol. So it's not the chi-squared, it's just chi-square, but the symbol has the squared thing. So be aware of that, because a lot of times people will write a chi-squared test, and then I'm going to yell at you. I won't take points off, but I'll yell at you. So there's 3 main reasons to use this test. To see if there's a statistical relationship between 2 categorical variables. That means measured nominally or ordinally. These variables have to be independent. Their categories have to be independent of each other. You can also use it to test if there is a statistically significant difference in proportion or percent of a dependent variable across categories in an IV. So if you have more than 2 categories, you can use this, but we don't usually use that. But I do show you an example, but I'm not going to make you do that on the homework. And then it's a test of goodness of fit of expected values, which I'm also not going to make you do on the homework, but we're going to talk about it. So really, we're going to learn this one. I'm going to talk about these, but you have to do this first one. So it's used to look at the relationship between two categorical variables. So the dependent variable is categorical, which means it's measured nominally or ordinally. And the imp IV is also categorical, measured nominally or ordinally. Some assumptions we're making with a chi-square is that there's no observation in more than one category. So you can't be in both of the DV categories and one of the IV categories. You have to be just in one. And when we get to one of the tables, it'll make sense a little bit better. None of the expected frequencies should be 0. So when we make the 2x2 table, there shouldn't be zeros in any of the boxes. And most, if not all, of the frequencies should be at least 5 in each box. And one example of a question that could be a chi-square is there a higher percentage of binge drinkers who are Christian versus those who are Jewish, Muslim, and Hindu? So here, the DV would be binge drinking status, measured as yes or no. And then the IV would be religion, so measured nominally as Christian, Jewish, Muslim, or Hindu. So that's just a question you could think about. So we're going to enter some data with the activity later into SPSS, but each row in SPSS will be one person. So for that example, we have one person, or this person said yes to binge drinking. We're going to say, wow, yeah, 1 equals binge drinker. So this first person said that they do binge drink, and then they are Christian because they answered 1 to this question of what religion are you? Then number 22 said they are not a binge drinker and they are Jewish. So each row here is one person. Does that make sense? Okay. So another way you'll often be presented the data for a chi-square is in this 2x2 contingency table. So here you have the IV in this top, across the top, and you have the DV in the 2 rows. So here we're asking if treatment method, or if sickness, so getting sick, yes or no, differs by taking vitamin C or a placebo. So what I was saying before with you can't be in more than one category, you can't be in the vitamin C and have a cold category, as well as at the same time be in taking vitamin C and not having a cold. You can't be in both of those at the same time. If I'm one person, I can't be sick and not sick at the same exact time. I either am or not. So you can only be in one, each person can only be fitting into one of those boxes. I could be taking the placebo and not get a cold, or some other person could be taking the placebo and get a cold. That's all that this middle part's saying. Then if we total up the number of people that took vitamin C and got a cold and took the placebo and got a cold, that is this row total. And then the same thing with this row total, except they would be all the people who did not get a cold. The column total would be all of the people who took vitamin C or all of the people who took the placebo. And then this bottom grand total down here in the corner would just be everyone in the total sample. So here is an example with real numbers. So is there a difference between the proportion of children developing colds within the treatment groups? So the treatment would be vitamin C. 36 children developed a cold, and 21 did not if they were taking vitamin C. How many people, I'm going to ask you, so you're going to have to answer, took the placebo but did not develop a cold? 11, yay! Good job. And how many people are in the total sample? 103, exactly. So that's what this table is telling you. And then here we also have the percent. So this is calculated by dividing this number by the number in the total sample. But again, I'm not going to make you do that. You might just see it in other literature that you are reading or in the future somewhere.
Isn't it dividing by 57?
Yep, sorry, you're right. It's down the column, not by the total. So these 2% should add up to be 100 because it's the total number of people who took vitamin C. And 36 or 63% of the people who took vitamin C developed a cold. Thank you. And then the same over here. 76.1% took the placebo and got a cold, while 23.9% did not. Okay, so continuing that example, oh look, that's what it says here. 63% developed a cold if they were taking vitamin C, and 76 did if they did not. So here our null hypothesis is that there's no difference between the proportion of children who develop colds versus those who don't, versus vitamin C versus placebo, sorry. And the alternative hypothesis is that there is a difference between taking the vitamin C and not taking it. So we're hoping that the alternative hypothesis is true because we want vitamin C to work better than not taking anything. That's what we're hoping happens. So again, we go to our hypothesis testing procedure, which is all these steps. So we define the two categorical variables and set our hypothesis. We did that on the last slide. Select the alpha level. This class, always 0.05. Then we take the data and make a table, which we did. Well, it was already done. Then, these are the steps that I'm not going to make you do because SPSS will do them for you, but I'm still going to walk you through it so you know what it's doing. Calculate the degrees of freedom from the row and column information. Find the critical value from the distribution table based on that degrees of freedom. Calculate the expected values, or if they're given, you can use those. Then you're going to calculate the chi-square and compare it to that critical value you picked up here. So all of those steps, SPSS will do for you, which is awesome. And then you'll just have to decide if you're going to reject or fail to reject the null hypothesis based on the results from SPSS. Makes it a lot faster, but we're still going to go through it so you know what's happening. So we set our alpha level. The degrees of freedom is the number of groups minus 1. So in this case, we have two groups, those who took vitamin C and those who didn't. So 2 minus 1 is 1. Then we go to the distribution table, which is in your book somewhere, but we're not really going to use it. And we get the CV, which is 3.84. Cool. Then we calculate the test statistic with the lovely formula. Isn't that great? Doesn't that look beautiful? We don't want to do that. That takes so much time. So we find out that the test statistic is 1.99 because magically we did all that math really fast. Since our test statistic is less than that critical value, we do not reject the null hypothesis. This means that there is no significant difference in this sample between taking the vitamin C and getting sick and not taking it and getting sick. So there's no significant difference here based on this sample. And then this is an example of how you would write that up in your homework. So just including the names of the variables as well as the percent, the chi-square, the degrees of freedom, the chi-square value, and if the p is greater than or less than 0.05. Okay, next example. Woo! Are smoking and alcohol status during pregnancy independent? So, does smoking cause alcohol consumption is kind of what we're asking, which is kind of a weird question, but we're going to go with it. So here, this is the formula for calculating the chi-square. Has all of the, if you have more than 2 categories, how to calculate the degrees of freedom. So that's the number of rows minus 1. So there's 2 rows. so 2 minus 1, times the number of columns. There's 4, so 4 minus 1. So 2 minus 1 times 4 minus 1 is 1 times 3, which means the total number of degrees of freedom in this example is 3. Whew. Then the expected frequency, so this bottom number down here, that just means if we were to take a sample and get a really large number of people, how many people would we expect to fall into each of those categories? So to calculate that, you use the row total, this value here, times the column total. So if we're calculating this first, smoking and not consuming alcohol during pregnancy, we would multiply 4198 by the column total, 6170, and then we divide that number by 11,127. When you do that, you get this value. And the same thing for across the rows and across this row also. So this is the value we have in our sample. If we were to take 100 samples, this would be the number we would expect on average to get across the samples. I know it's confusing, but this is what happens. SPSS does this for you, so again, just behind the scenes here. So now we're going to identify the DV, smoking status during pregnancy. So the DV is always these two rows here, and the IV is always this top, the things that are in the columns. So the IV is alcohol consumption during pregnancy, and this is measured ordinally because not drinking any is less than drinking a low amount, which is less than drinking a medium amount, which is less than drinking a high amount. So there's an order to those categories, so it's ordinal. And there's 3 or more of them. If there were only 2 categories, none and some, it would be nominal. But since there's 3 and they're in an order, it's ordinal. Okay, so we're asking if there's a relationship between these 2 variables or not. So our null hypothesis is that there is no difference, and our alternative hypothesis is that there is a difference. Alpha level, we did the degrees of freedom already, so that's 3. We go to the little table with the degrees of freedom and find the critical value of 7.815. Then you put all those fun numbers, the value in your sample minus the expected value squared, divided by the expected value for each box. So if you look at these and look at this box, you see that there's one calculation for this box, and there's another for this, and another for this, and another for this, and so on, so that there's 8 sets of information here. So this first 1, 2, 3, 4, 5, 6, 7, 8. And when you calculate all of those, and then you add them together, bam, you get 338.7. That is really a lot higher than our critical value of 7.8. So we reject the null hypothesis, which means there is a statistical difference between smoking, or between alcohol consumption level and smoking status. Does that make sense? Kind of. Then the other thing you can do is calculate the percentage, which we will have SPSS do for you. But we always are going to calculate down the column because it's more meaningful than across. So our conclusion for that chi-square is that the percentage of people who smoke during pregnancy increases with the rise in alcohol consumption during pregnancy. So there's 30.5% that smoke in the non-alcohol group, and 45.7% in the low alcohol consumption, 53.0% in the medium, and 67.3% in the high. So these numbers rise. Smoking increases as alcohol consumption increases, is what this is saying. And then you put in your values here. Does that make more sense now that you can The percents help you see what is actually happening versus just the number of the chi-square. Okay, more examples, yay! Is the percent BMI breakdown of your Northeastern California Safety Net Clinic children aged 12 to 19 statistically different from the set of data from Kaiser Permanente, which is a big organization that does research. So they have this list of standard BMI levels for age groups. So we're going to compare our clinic, our range of BMI values to that national standard of values. So in this case, we know the expected frequencies because we're comparing them to this national standard. So we don't have to calculate them. So now we can see if there's a fit between our data from our clinic and compare it to that national standard. So we're not going to actually do this, but let's just say this is what you came out with. So the total number in our sample is 250, and the sample for the Northern California section of this national sample is 234,120. So here we have the percent of people in our sample that's underweight, as well as those in this sample, big sample, that are underweight. These numbers in parentheses here are the confidence interval. So we talked about this last week, developing that 95% confidence interval. So these values tell you how close that range is. So if you look, our clinic falls outside that standard range for Northern California. Our healthy weight also falls outside the range because it's less than this lowest value of healthy weight individuals. Our overweight is above the standard here in Northern California, and our obese is also above the standard. So what does this mean? What do you think it means? Any guesses? Or maybe not guesses, thoughts? So what is this table telling us about our sample compared to this population of Northern California national sample?
Doesn't seem that high.
Okay. Why do you say that?
Because the first two are pretty much very close. The percentages just seem to be close for the most part.
Okay, that's a good reason, but what we want to see ideally would be our ranges fall between these two values in this confidence interval. So then we would have the exact same population in our clinic as represented in the entire clinic, or the entire area of Northern California. So what we're really seeing here is our clinic is more overweight and obese than this sample from all of Northern California. So more of our patients at our clinic are obese and overweight than the whole area of Northern California. So that's what this is telling you. Does that make more sense? Okay. So this example is from your book, but I thought it was helpful to see something step-by-step from your book, and then I also have the data for SPSS, so I can show you how an example hand done compares to how it does on SPSS. Ready? Cool. So children represented with a picture of either an angry or a happy face, and then they were given an opportunity to select toys of 3 different colors, and we recorded which face they were shown and which color toy they picked. So what is our independent variable? Face? Face, because, well, one we aren't going to say because it's on the top of the chart here, but for your homework you'll have charts too, so it might be a little bit easier. And what's your dependent variable?
Hungry and healthy.
Toy color. How are these measured? Nominally, ordinally, or continuously? Nominally. So face is measured nominally as happy or angry, and toy color is measured nominally as red, green, or gray. Since these are not ranked, it's still nominal. Okay, and then here we had 15 children who chose a red toy after seeing a happy face, and 6 who chose a red toy after seeing an angry face, and so on. So then we're going to state our null and alternative hypotheses. So the two variables are independent, there's no relationship between them, and our alternative hypothesis that there is some relationship between which face they saw and which color toy they picked. Then we calculate our degrees of freedom, so the number of rows minus 1 times the number of columns minus 1, which comes out to be 2. Then we set our alpha level, which is 0.05, use our degrees of freedom, and find that critical value on the table, but you're not actually going to do this because SPSS is going to do it for you. But that's what you would do if you were doing it by hand. So now we're going to say if the chi-square value that we find in our calculation is greater than 5.99, we will reject the null hypothesis. Otherwise, we will not reject it. Dun, 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 dun. So now we're going to calculate the expected frequencies, the row total, so that number all the way on the right of the table, times the column total, the number on the bottom, divided by the total number in the sample. Ta-da! It's done! So here we have the number that we saw in our sample and the expected frequency if we were to take 100 samples from the same population. Then we're going to use this lovely formula here for each of those boxes in the table. So R value minus the expected frequency value squared divided by the expected frequency, and then add them together for all of the boxes. And eventually, after you do all of that math, you get 8.24. So what does this mean? 8.24, our chi-square value, is greater than 5.99. So therefore, that's what this little dot symbol means. Therefore, we reject the null hypothesis. So we're saying that there is a difference, there is a relationship between the colored toy they picked based on which face they saw. So here it's written out in a really, really long sentence, but that's basically what it's saying, is that they depending upon which face they saw, they may have chosen a different colored toy. And then our values are listed here. Again, the chi-square with the degrees of freedom in parentheses is equal to the value of the chi-square we found. And then since this value is greater than our critical value, the p-value is less than 0.05. Does that make sense? Figuring out how to reject the null hypothesis, and if you reject the null hypothesis, p is less than 0.05. If you accept the null hypothesis, or another way to say it is fail to reject the null hypothesis, then the p-value will be greater than or equal to 0.05, which means there's no statistical difference. So for that same example, I did it in SPSS. I'm not going to switch over because it makes the video get messed up and then you can't see anything, but I have the output here. So what you can see is this top box just tells us that there were 40 people in the sample, and it was all of the people in the data set were used in this analysis. There were none missing. Remember, if you have missing people, something went wrong in your data set. You don't want to have any missing people for this class. So now this table here is very similar to that table that we produced, that I showed you a couple slides back. So here we have the choices between the expression of the face they saw, happy or angry, and we have the 15 children that chose the red toy, and the 6 that saw the angry face and chose the red toy. And then here's the total for the row, and then here's the total for the column, and then we have the percents going down the column. So there were 10% of the children who saw the happy face chose the green toy, while 35% of children who saw the angry face chose the green toy. Does that make sense? Reading that makes sense to everyone? Okay. So this is the other part that comes up. After this, I just made it 2 separate things so you could actually read what was on the screen. So the things we need to know is this first row. We're not going to care about the likelihood ratio. That's something we're not talking about in this class, but it makes it anyway. The linear by linear association, I don't even know what that is, but we're not doing it in this class, so ignore it. The number of valid cases. This should equal your total sample size. So we have 40 children that were in our sample, so that's 40. So here, instead of calculating that value with that huge formula that took up half a slide, it just tells it to you, and you don't have to do anything except push a couple buttons. And it also has the degrees of freedom, which is what you need to include in your write-up. And then instead of looking at the critical value to determine if it's significant, you look at this sig value, which is the same as the p-value. So since this is less than 0.05, it's still showing that there's a significant difference. So that's what SPSS output for a chi-square looks like. Any questions about that? Next is McNemar's test. So this is very similar to chi-square. The only difference here is that the people in the sample are usually the same, and you have a before and after design. So it's kind of like that paired t-test where you're measuring people before, program, and after. So the DV is dichotomous, so they're either yes or no, and they either have or don't have some characteristic that you're looking for. And then the IV is paired groups. So testing time, pre to post, 2010 to 2015, things like that. Or matched pairs, which again, I won't make you do in this class because it gets really confusing. Does that make sense? So the only difference between the McNemars and the chi-square is that both can only be dichotomous, so they can only have 2 values in their categories for the variable, and the IV has to be a paired grouping. So you enter this the same way you would enter the data for a chi-square. Each row is one individual. So in this example, the pre-seatbelt, so before an accident, maybe these people did use a seatbelt, and after they had an accident, they still used a seatbelt. Number 70, this person did not use a seatbelt before they had an accident, but now after their accident, they use one. The number 63, I know I'm going backwards, but this person used to use a seatbelt, but then they had an accident, so now they don't use a seatbelt. Interesting. I don't know. So we have 100 people in this sample here. So this is the same example, just with more numbers. So after we entered all that data, SPSS told us there are 60 people that said that they used their seatbelt after an accident and before the accident. There were 19 that did not use it before the accident, but did afterwards. There were 6 that did not use it after their accident, but did before. So that's kind of weird. Those are the people you're like, you used your seatbelt, you had an accident, but then you stopped using it. Interesting. Okay. Then this last box would be people who didn't use a seatbelt before an accident and still do not use a seatbelt. And then again, the totals are here. This is the formula. Again, I'm not going to make you calculate this. You would just need to identify, if I gave you a scenario, of a situation and say that it was a McNemar's test instead of a chi-square because the DV was dichotomous, had two categories, and the IV was dichotomous, had two categories that were paired. So you're not going to have to calculate this in SPSS, but you will need to identify this in examples. But this is the write-up for a McNemar's test. If you see it somewhere, this is very similar to a chi-square. So it uses the same chi-square symbol and the degrees of freedom, then the value found, and the p-value. This is another example of seeing pre-test to post-test scores of getting some knowledge item. They got it incorrect before the class they took, and they still got it incorrect after they took the class. Then number 3 got it incorrect before they took the class, but after they took the class, they got the question correct. So maybe you have like 10 items like that. You would enter each of them before and after, and then you could use this McNemar's test to compare and see if they increased their scores. The kappa statistic is if you are doing inter-rater reliability. So if you're doing qualitative studies, you want to see if your people that are classifying the data into different groupings or categories are doing it in the same way. You would use this kappa statistics. It ranges from -1 to +1, and the higher the positive value, the better the reliability, which means they're rating things in the same way. If the value is closer to -1, it means they're not coding the information at all similarly. There's no relationship between what one person is doing and what another person is doing. So we would like this to be closer to 1 if we want them to be coding information the same way. And if we had more than 2 options, so maybe they're coding some items similarly, some items differently, and some items they're not using, maybe. That's not ordinal. I don't know. There was 3 categories here, so maybe I don't know. If they had ordinal data though, you would use a weighted kappa, which is even more complicated, so we're not going to talk about it. Okay, so a couple of journal article reviews, and then we'll do the fun activity that actually makes you move so you don't fall asleep. So this first one is talking about dog owners' increased level of physical activity. So here, this first column are demographics and physical activity levels for people who own a dog. And then this other column is for people that do not own a dog. And then in this last column, you have p-values. So what I don't like about this is they don't give you the chi-square value. So you don't know what that number is. You just know if there's a significant difference between dog owners and non-owners of dogs. So for example, there is a significant difference in males between dog ownership and not. 36.1% of dog owners are male, while 44% of non-dog owners are male. So that means there's more male dog owners than more male non-dog owners than male dog owners. Interesting. And the same thing with physical activity levels down here. Then this one is comparing lifestyle behaviors between Caucasian and Asian Americans. So this first column is the total sample, so everyone that they surveyed. Then the second column is Caucasian, and the third column is Asian American. Then here they have both chi-square and independent t-tests. So the independent variable in this case would be all of these down the side here. So women, age category, married, annual income, high school graduate, which would be education level, employment status, current smoking status, binge drinking status, weight, physical activity level. And then the DV would be Caucasian versus Asian American. So, depending upon lies, reverse that. The DV is ethnicity, and the IVs, no, these are the DVs on the side. Sorry. These are all the DVs, and this is the IV. So, since age here in this first line is measured continuously, and then our IV, ethnicity, is measured nominally, what test would they use? Independent t-test, yes. So this value here in this column is the value of t that they found, which is 2.86. And then the p-value is the significance level. So they found that it was 0.004, which means there is a significant difference in age in this sample from Caucasian to Asian Americans. I know. Isn't that crazy? So it's the same for all of these. So women here in this example would be a chi-square value because women, it's basically saying women versus men, so not versus, but those are the two categories. So they're measured nominally. And then white versus Asian American, so that's also nominal. So it's a chi-square since both the DV and the IV are measured nominally. So the chi-square is 0.08. The p-value is 0.779, which means there's no significant difference in ethnicity related to gender in this sample. Cool? Cool. So now we're going to do some SPSS stuff. Yay! So if you don't already have it pulled up,